So this is the ejector of CAREL, okay? So we have our body. The gas cooler flow comes from this direction, and we have the suction coming from this direction. If you see, also the geometry of the ejector would allow the suction from MT to be more fluid inside the ejector. And here it is what we call our cartridge, and it works with the same principle as bipolar drive. In fact, this motor is like a bipolar that CAREL manufactures. And here you can see that I have the needle, and the needle is controlling the amount of refrigerant flow that can passes through the ejector. So this needle can go up and down and make sure that we have the precise refrigerant flow that we need for that specific application. And this is what it is controlling. And the ejector will take effect from this part, from the suction line.
Welcome to another CO2 Expert Live. Once again, thank you for taking the time to come and join us on these live session. If you're listening on the podcast afterwards, I'll try my best to explain some of the slides. If not, go check out the YouTube channel, Refrigeration Mentor YouTube channel. This will be up there in a little bit. And plus the social media, check out the LinkedIn's or Instagram posts that we put. I always take cutaways. I've done a ton with Marcel before on their CO2 compressor. And it's really important to invest in yourself and share this with other people. This is the big thing. So if you learn something here, go talk about it with somebody else. This is what I talk about all the time in our CO2 training programs, supermarket program. The things that you learn, go and try to share that knowledge and talk about it, because you got to see things 7 to 11 times before you really start to grasp it. And today we're going to be getting into ejectors, and we're going to be talking about different ways to do refrigeration. And I'm with my good friend Marcel. He is an expert at refrigeration. He's been supporting technicians and manufacturers from all around the world for a long time. And he's definitely an expert in his field. I'm super excited for this conversation. Marcel, welcome to CO2 Experts Live. How you doing, brother?
Hey, Trevor, thank you for having me here. It's always a pleasure to talk to you and share a little bit of our experience with CO2 applications.
So let's dive into it, Marcel.
Okay, so just to give you a little bit of context on what CAREL is doing with natural solutions. CAREL is a company that it's an Italian-based company, and we have been doing natural solutions for a while now. Like the Transcritical solution that we have has been in the market for over 15 years now. And this is data from 2022, but I think today we should be around 14 or 15,000 installations around the globe. So, and many of these installations done here in the US. So this is just to share a little bit what CAREL is doing in terms of application and what we are investing in terms of new solutions. So natural solutions is something that for us makes a lot of sense, and we invest a lot of efforts both on R&D and also in products to have the best technology as possible for that. Diving into our CO2 solution, we have a very wide range of capacities, from very small condensing units to the big racks. Today, I want to spend some time talking about our modulating ejectors. So a different type of ejector that you guys will see in the market. There will be the PWM versions, the fixed type versions, and ours are the modulating ones. So I want to go in deep and explain a little bit how it works, where it's installed, and mainly why you should use an ejector on your transcritical system solution, if you like, okay? So talking about CAREL as ejector, this is not a new technology for us. We have been selling ejectors and developing this project since 2016. So we have collected a lot of tons, a lot of feedback on this application, and we are very confident that now that we are bringing this product to the US, it will be a huge success, and it will be an easy installation from our customers. Couple comments on the ejector. So our version of the ejector is a vapor ejector only. So basically, we admit low superheat refrigerant, but not only liquid, okay? And another difference on our ejector is that it's a modulating ejector. So we have an internal motor inside the ejector, and with this motor, we can modulate the refrigerant flow inside it. And with that, we can reach the precise need for the system. So let's say the first feature or the first requirement of the ejector is to work as an HPV valve, so a high pressure valve. And a positive side effect is that we can use all this energy that we are expending the CO2 throughout the HPV or the ejector to make a small compression from medium temperature refrigerant flow, okay? And these logics are controlled by two different types of controllers. We can use the PRAC, our standard rack controller for transcritical solutions, but CAREL is also bringing to the market a new product called the Ejector Manager. So imagine a dedicated controller, a standalone, that you could use it to drive CAREL's ejectors, PWM ejectors, and make it integrated to any type of control. So it could be CAREL, could be any other brand of your preferred compressor control logics, and it will be working seamless with all these type of technology. Okay. So talking about a little bit about ejector, why is it an ejector and how it should work? So let's start from the beginning. Normally, when you have a compressor, you have the electrical power, so the energy coming from the electrically, making the compression from low pressure to high pressure side of the system, right? So you inject electrical power and then you make the compression. When we have an ejector, the difference here is that instead of having the electrical power as the main source of energy to make the compression, we can use the expansion of the refrigerant. So we are basically using the high pressure side of the transcritical system to make a compression from the low pressure side. I will explain this better here in the next couple of slides. But the idea here is that we can basically free compress refrigerant without needing to add more electrical energy to that. So this is the main point. So we can be like energy saving when the system is performing at high pressure. So a lot of people ask me, what technology is better? Is it better to have an ejector? Is it better to have like a subcritical system? What if? So normally my answer for this type of question is that when you have a system that needs to operate at high ambient temperatures, like Phoenix, Arizona, where you have very high temperature for a certain period of the year, every system down there will have a higher energy consumption. So what we can do is improve this energy consumption, adding some other technologies that can make more efficiency for the same energy power that you are consuming. If you compare an transcritical system with ejector to a subcritical system, subcritical would always be better, but not always you can get these, like warm regions, Florida, even Phoenix, Arizona. So all these regions where during summer you have high ambient temperatures, you cannot operate with subcritical at that region. So ejector comes and makes a better effect on that type of region.
Yeah. Okay. So I did when I was at the AHR show, I did a CO2 talk on high ambient strategies for retailers. And the biggest thing is that in our CO2 design course, because we train designers from all around the world to design CO2 systems, we discussed that there's different strategies for different climate zones. So you can't just say this is going to be one strategy that goes here and this one goes here, and it's always like that. It's you got to put it into design to see if it's going to work. And so ejectors is great for high ambient. So I'm here in Canada, right? So ejectors may not be the solution for a retail, like a supermarket system, you know, because we're in subcritical most of the time. Ejectors you want to have high pressures, high temperatures. But we'll may get into it a little bit when I talk with some manufacturers. They're like, well, if we're running on a CO2 heat pump, we're in transcritical all the time. So ejectors may be a good option for that in Canada. So we'll dive into that later. But this is the thing. You want to really understand the different high ambient strategies. Ejectors is definitely one for really hot locations.
That's correct. So going into the ejector, so what is an ejector? Ejector, in our case, it is a device that we can take a positive effect of the refrigerant at higher pressure. So when you have a refrigerant at higher pressure and higher temperature, and you need to expand it, you can basically speed up the refrigerant inside this device, the ejector. And when we have a refrigerant at higher speed, you also create what we call a low pressure zone. So a zone inside the ejector where you can create a lower pressure and you can start dragging refrigerant from the medium temperature area. So if you see here in the picture, we have the three main components. We have the gas cooler pressure, the gas cooler outlet temperature that is defining, and the mass flow that comes from the gas cooler. Once we have a very high mass flow here and a very high pressure, this expansion from the high pressure side to the liquid receiver causes this what we call Venturi effect, so a low pressure zone. So we are able to start dragging part or total refrigerant from the medium temperature line, so medium temperature pressure and suction, through the ejector and making a combination of that. So this is the very basic principle of the ejector operation conditions. And in our case, we also have a third variable that here, that is the opening degree. So since we have an ejector that can open and close, we can control this mass flow, controlling the gas cooler pressure at an optimal point, so even during summer conditions. And this would allow us to make the system controlling the pressure and as a positive effect, dragging refrigerant from the medium temperature lines, okay? And as I mentioned, we have an ejector that is a vapor-based only. So the geometry of the ejector are optimized for dragging vapor only. It would work if we have small droplets of liquid inside the ejector, so low superheat, but its maximum efficiency, so maximum capacity of dragging refrigerant occurs when we have just vapor on that specific line. So as a general rule of thumb and recommendation, we would like that here at the inlet of the suction port of the ejector, we would have a superheat higher than 9 F as a reference, okay? So it means that on the case side, you could have a lower superheat, because then from the case until it comes to the rack, you could increase a little bit this total superheat, okay? So coming internally, I have divided this presentation in couple parts. So thinking about the motive or the gas cooler pressure. So the inlet from the gas cooler, what we have there, we have a higher pressure normally during summer conditions or warm ambience or heat pump application with a certain gas cooler outlet temperature. So the main function of the ejector will be regulating that pressure, acting as a HPV valve. So in the case of CAREL ejectors, we can totally replace the HPV valve with an ejector. You don't need to have two different components. And this is mainly because the ejector is able to control the pressure on the gas cooler. Okay, so I have a refrigerant with high pressure and high temperature normally, passing through an expansion, because the high pressure valve is an expansion device. And during this expansion, we are also increasing the speed of refrigerant. So I create here a mass flow with high refrigerant flow that would generate some dragging effect. Okay. On the other port, on the suction port, coming from the medium temperature suction line, what we have a refrigerant, let's say around 400 psi as a pressure for medium temperature applications. And basically, when I make that expansion, I generate here at this area, as you can see here, a low pressure zone, and the refrigerant as current will always go to the easiest path. So if the pressure is lower here, it will prefer to go through this path. So we create this zone with low pressure conditions that the refrigerant flow will be preferred to come to this direction, okay? And at this point, what we are doing here, we have a mixing area. So I have high refrigerant flow with high speed and high pressure, reducing the pressure. And I have this refrigerant coming from the medium temperature, low speed, and increasing the speed. And here what we come to an average pressure that normally is the liquid receiver pressure from this combination. So I'm basically mixing the refrigerant that comes from the gas cooler and the refrigerant that comes from the suction port. We are mixing this inside the ejector, and we are creating, as a consequence, the liquid receiver pressure and mixing of CO2 refrigerant, okay? So in this case, gas cooler pressure will reduce the pressure and increase the speed. Suction pressure will increase the pressure because we are compressing it from 400 psi to a higher liquid receiver pressure. Normally, I would say 460 to 500 psi pressure range. So we are making a compression, and we are increasing also the speed of this refrigerant, okay?
So before we go on, Marcel, just
Yeah.
so people that are listening on the podcast, basically the pictures that Marcel showed, you have the high pressure coming from that gas cooler. So it could be 1200 PSI, it could be 90 bar, whatever coming through there. And then on the outside of it, we have that medium temp suction, just like Marcel said, that is being pulled in there from the high pressure. And then now you have that mixing section that's going into your flash tank, your liquid receiver, or your vessel. So thank you, Marcel.
Yeah, and that's a good point, Trevor. Thanks for reminding me. And why the ejector is, let's say, we designed the ejector for high ambient temperatures, because at higher ambient temperatures, normally we also have a high pressure related to the gas cooler, right? And as higher as this delta pressure from the HPV on the gas cooler to the liquid receiver, higher is the capacity of dragging more refrigerant. So if you apply an ejector into a subcritical condition or in a mild or cold ambience, the ejector will be working as a high pressure valve, regulating it, try to control the pressure on the gas cooler, or even making some subcooling. But since I have a very few delta pressure between the gas cooler to the liquid receiver, the capacity or the capability of dragging refrigerant are reduced. So the ejector effects are not there anymore, and the refrigerant will go through the normal empty suction compressor line, because at that point there will be more lower pressure than the ejector point. Thank you for making this comment.
Yeah, no, that's great, because you need that high pressure to drag it, like you said. If not, and just say it's the middle of winter, it's just going to work as a high pressure valve, just like you see out there today.
Yeah, that's correct. So we are making the mixing here, and we have what we call momentum transfer. So I'm using this kinetic energy from a refrigerant at higher speed to drag and compress the other refrigerant. So at the end of the day, the total amount of energy is the same, but we are basically transferring the energy coming from the gas cooler refrigerant to the MET suction line to increase its pressure. So no magic here. It is just transferring the energy between the two different fluid conditions. And as a consequence, we have here the total flow that goes to the liquid receiver. And you might be asking, what is the advantage of making this compression? I mean, why should I increase the amount of gas that I'm putting inside the liquid receiver, right? So the point here is that you could use some piping diagrams, I will show you later, to make the compression not from the compressor perspective, not from like the suction and MT 400 psi, but from the liquid receiver perspective. So all your compressors will be working as a parallel compressor. So you have a higher suction pressure, same discharge pressure, we cannot change that, right? So since the pressure compressor ratio is decreasing, the amount of energy that you need, or mainly the amount of compressors that you need to have on to make that compression, can be reduced. So that's where it comes the savings in terms of energy, because I'm getting a refrigerant at higher pressure to the compressor, so the compressors will work less in terms of effort to make the compression.
Yeah. So for all the people that have been in my CO2 training pros, we talk about that. So you have that cycle. You got compressor to your gas cooler, high pressure valve through a flash gas bypass valve back to the compressor. So there's really no work being done, but there's a lot of energy, especially in the middle of the summer, you need more compression to pump all that flash gas. Now, when you have an ejector, instead of putting all that energy, just like Marcel said, right into those compressors, now you're doing that less work. So you don't have that large compression ratio. And that's what we talk about. This is even in HFC. We want to reduce the compression ratio as much as possible. That reduces the work and reduces the energy. And that's kind of what the ejectors are doing. Yeah.
And also as a positive effect, Trevor, we know that CO2 transcritical sometimes could be a little bit challenging, because during summer you need an extra capacity for the compressors, and during winter you have too much compressors that sometimes it's always hard to regulate the rack at that subcritical conditions. Using the ejector, you might be able to reduce the amount of compressors, or at least reduce the sizings of your compressor, since you would need less compressor during summer, and this would make your system more stable, because when you have a smaller compressor, you have more flexibility in terms of modulation. So you can reach that specific point to maintain the system running and the compressor on most of the time.
Yeah. And this all goes back to design. So this, if you're a technician out there, this is not what you got to worry about. The manufacturers that are listening, though, it goes back to design. Do you meet every gap as if you're using ejectors into different compressors? Because if you go with too small of compressors, maybe it had too big of a gaps, or all the same size compressors, you may have big gaps. So this goes back to the design when you're using ejectors, and they got sizing softwares out there. I've seen, you know what I mean? So you can go into the sizing if you're a manufacturer and really plug it all in, because you got to know the ambient, you got to know the climate. There's a lot to it as a manufacturer, but when it's done right, it works really well.
Yeah. So here I'm just showing you again what we are doing in terms of fixed conditions, and consider that this example here, this first picture, are considering what we call a fixed ejector behavior. So there is no device metering the amount of flow from any of the parts. So what CAREL does when we have modulating ejector, we add here a needle inside the flow that comes from the gas cooler side, and this needle will be used as with a stepper motor to control the flow inside the ejector. So with this needle, it is what gives us the capability for the ejector to act as an HPV valve in all the conditions. So this needle will be controlling the gas cooler flow over to the liquid receiver, and will be adjusting the pressure according to what's needed. Let me show you here very quick what we are talking. So this is the ejector of CAREL, okay? So we have our body. The gas cooler flow comes from this direction, and we have the suction coming from this direction. If you see, also the geometry of the ejector would allow the suction from empty to be more fluid inside the ejector. And here it is what we call our cartridge, and it works with the same principle as bipolar drive. In fact, this motor is like a bipolar that CAREL manufactures. And here you can see that I have the needle, and the needle is controlling the amount of refrigerant flow that can passes through the ejector. So this needle can go up and down and make sure that we have the precise refrigerant flow that we need for that specific application. And this is what it is controlling. And the ejector will take effect from this part, from the suction line.
So I can't see on there because it's not zoomed in, but is there a screen or anything there? Because I know there's a lot of high pressure valves that like in our CO2 trains, guys are sending me pictures, and the high pressure valve is just gummed up with stuff that shouldn't be in the system, you know, on carbon and stuff. Is there a screen on that one? I couldn't see or not.
No, this specific one, we don't have it, so it's an open area. Yep. So when we are designing these systems with our customers, we always recommend them to have a filter prior to the ejector inlet. Yeah, so there is no need to have like a process to run the system before activating the ejector during a commissioning, but you would be recommended to have a filter before the ejector to restrict any dirtiness that could be inside the system. I've been into some sites and I can testify what you are saying. Most of the times we might find a couple of dirtiness inside the system. So filter before the ejector is highly recommended, or even not mandatory, to the better performance of the system.
Yeah, and that's in your instruction manuals too. It recommends that, and this is something that we're not supposed to have dirt in the system, but it consistently happens. So make sure you protect the most important components. And if you have your high pressure valve go down, you're going to have on your CO2 system, you're going to be in a big trouble for that day. That's for sure. So make sure you always check that. And that's there. And most manufacturers are doing it. You know what I mean? I've been to dozens and dozens of sites, and they have strainers or filters ahead of them. So thank you for that, Marcel.
Yeah. So, and how we control this needle? We have here the stator. So it's the same as our electronic expansion valves.
Lower, Marcel. It's just blurry. No, lower. Yeah, there we go.
Here.
Down. Yeah, right there.
Okay. Yep. So we have our stator is the same as our stepper motor valves for the electronic expansion module. And this motor can be connected to a bipolar driver, CAREL driver, and we can adjust precisely the flow that we have inside the ejector. Okay. Let me come back to the presentation, and then we can talk more about all the other stuff. I have a lot of small things here I want to show you guys today.
Yeah, thanks for sharing that. That's the first time I've seen it. I've seen them at the show before, but I never seen them apart because for some reason at the shows they're all screwed in tight. So thank you for sharing that.
So here, and we have this moving needle making the adjustment of the flows. Okay. And this is the spec of our ejector. So it's a device for sure rated for higher pressures. You can use into transcritical conditions, no limitation. It has the same protections as our electronic expansion valves. It's well certified. So we are really ready to start this product inside the US market. I can tell you that we have multiple OEMs testing this into laboratories. So if you are a technician, be prepared, but for this year, most probably, you will start seeing more and more ejectors in the field. We have a couple installations already done, and you will see more and more this technology going. Now that the OEMs got the knowledge about transcritical system, they are trying to improve their units with like ejector technology.
Yep.
Okay, and talking about the system, so I have my compressor pack there, I have my rack. Where should I install the ejector? How should I pipe it? How should be installed and so on? So basically here I put a diagram on how to install an ejector or how the ejector will be installed when you see in the field. We have our empty compressor line going to the gas cooler. You see that I put just the main component. There are many other like filters, oil separator and so on, but main components. And then from the gas cooler, we have the ejector coming into the, from the gas cooler, we have the pipe coming into the ejector here. So as I mentioned, the main function of the ejector will be working as a high pressure valve. So during the, all the conditions, ejector will be controlled. So the logics residing in the PRAC or in the ejector manager are prioritizing the control of the gas cooler pressure here, okay? So we are making the expansion. And here you can see that my MET cabinets, so MET cases, the line is split into two different pipings. One that goes to the suction MET, combining with the LT line, and the other is coming from the MET cases and going to the ejectors. If you see here, we have two new components here, two check valves. And why we have these check valves here? Because of the effect of the ejector. So during summer, here, this zone we will be calling as a low pressure zone. Let me just go, then I will come back. During summer, we have this low pressure zone here. So we have a higher pressure on the ejector. I put here 1300 PSI, just as an example, and 460 on the liquid receiver. So I have a big delta. So it means I have a lot of energy to be transferred to the suction line. So I have a low pressure zone here. And the preferred path for the empty flow will be going from the cabinet to the ejector port. So during summer, I can also get 100% of the flow from all my empty cases going, empty evaporators, cases, walk-ins, going to the ejector port here. So I'm having a free compression. And then from the liquid receiver, like 406 PSI, going straight to the compressor. We will see that we have a dedicated flash gas bypass logic to make sure that when we are engaged, so ejector mode, the flow here will have a very, very low pressure drop at the flash gas bypass valve. So all the refrigerant will go here. And at this point, this suction pressure will be higher, and we need a check valve here to avoid flow back from the empty line to the empty suction cases. So this is the reason why we have this check valve here, okay?
Yeah, it makes sense because you're running your medium temp, say 400 PSI, and that's 460 coming from the ejector. So you don't, it totally makes sense.
So we can increase the pressure on the MET suction line, and we start getting more benefit from the ejector. And on the other side, when I mean during the winter, I have like a mild condition on the gas cooler. So here I'm saying like 800 PSI as an example. It could be any pressure. Then I don't have that much energy to be wasted here on the high pressure valve during the expansion. So I cannot have a lower pressure zone here. So at this point, the suction here at the compressor side will have a lower pressure. So The preferred path for the refrigerant will be going here, right? And not going on the ejector directions. And at this point, this check valve makes more effect because I would avoid the flow back from the ejector. Remember that I have the needle controlling the flow from the gas cooler, but here from the liquid receiver and this port, we are pretty much at the same pressures if I don't have the ejector effect. So I would have higher pressure, and this check valve would avoid fluid back. So you can see that from a component perspective, adding an ejector to your system, we just need to have more pipe because we need to connect the suction line to the ejector port and two different components. No complexity here. It becomes the very same booster system that you guys are normally able to see in any transcritical rack.
Yeah.
Okay. Let me just come back here. And so another positive effect with using CAREL ejector, it is that everything is done seamless. So you don't need to go there and change a parameter to make it ejector mode or make it traditional booster rack mode. It will be done accordingly to the external conditions, and the system will be adjusting ultimately by its own. So when the ejector can be working, it will work because I just have mechanical components, check valves here. So less failure points, less wiring things to check during a troubleshooting. And everything here is like basically thermodynamically done. So it will operate to one side or to the other in a simplistic way. In the past, we had like more complex logics with more components, but this is the past. With this new simplified layout, it makes much more easier for the technician and also easier for the design how to make it connected and make it more efficient. Okay.
Yeah, no, and that makes sense. Like the biggest thing is that if you're working on booster systems today and you have an electronic valve as your high pressure valve, this here is just another high pressure valve. It looks a little bit different than maybe what you're normally looking at, but it's the same as it's the same. It's just it's a valve that's opening and closing by an electrical signal by a couple of different sensors, pressure sensors and temperature sensors, to say we need to open up a bit more, we need to close off a little bit more. That goes back to a controller. So this is why understanding controls is so important. We talk about this in our CO2 trainings. Is important. Find out about that controller, understand how it was set up. You know, a lot of times when a system is set up as well properly, even with this, like an ejector maybe new, if it was set up right the first time, you don't need to go in and start playing around with the parameters. Right, it's usually a mechanical issue that's happening. There's an issue like a plug strainer or something.
Yeah. And thank you for mentioning about the software. This is another advantage on this new layout is that the ejector functions are already present on the standard software. So no new custom software dedicated just for ejector. Since the ejector is mainly operating as an HPV valve, you will see the ejector's percentage opening and close as the HPV valve. So from a technician that already knows CAREL controls or have already interacted with CAREL systems, it will be easy going because there is no special software for that, and it will be everything in the same package. For the new solutions with the Ejector Manager, there will be a dedicated controller where you can check all the electrical, all the parameters and everything related to transcritical valves control, and one of these valves would be the ejector one. Okay, and okay, so I showed you how it works on the mechanical side, but how the controls understands if it can increases the pressure, decreases the pressure, speed up the compressor, speed down, and so on. So how this magic occurs. This is done with the software with an addition of just one pressure probe additional to what the standard system is. So if you see a traditional system, you have a suction pressure probe here connected to the MET line that could be the same as the discharge LT, same pressure here. We normally have this pressure probe controlling the compressors, and then we have this P2 pressure probe here, so the liquid receiver pressure probe controlling the pressure and driving the flash gas bypass valve. Okay, so this is the standard booster system. What we add here, since we have a check valve and this pressure at the cabinet or cases could be different from the pressure here at the suction side, we add another pressure probe here called the cases pressure probe or cabinet pressure probe. So it means I'm monitoring the pressure that comes from the sales floor, so from the cases, to understand if my pressure is regulated at that point or not, independently what I'm seeing here in the compressor, since it could be a little bit higher. So basically what we have, CAREL controllers, it has a internal logic to monitor these two different pressure probes with two different set points and make sure that the compressor will be always engaged in maintaining what requires more capacity. So in case if this pressure probe here, the cases are not satisfied in terms of pressure, like I'm not hitting here the 400 PSI that I need, the compressor will speed up because I have a loop here looking for this pressure. And if this is satisfied, I will be controlling from the suction pressure that could be at higher set point. So this is what I get the most efficient. So standard MT pressure probe, and the P3 here, the P1 here, the additional pressure probe that we will add. So you'll see I'm adding more efficiency to the system, less complexity on the mechanical side, and less complexity on the electronic side. It's just one pressure probe that we are adding to this system. And from the case perspective, you could have any controller in the case, anything in the case that you don't mandatorily need to have it connected. If you have it connected, we can have better efficiency, better performance, but it's not mandatory. You could have this connected to CAREL controls or to third-party controls. So we are really flexible in the way we are controlling things, so we can provide the maximum flexibility to our customers.
Fantastic.
And so the capacity of the compressors, they will be managed independently by these two different probes, P1 and P3. And we are always making sure that we are satisfying pressures on both ends. So for example, it might come, depending on the type of the system, that my MT load could go to defrost, so I don't have requirement from MT cases or evaporator, and I still have load from LT. So I can keep my pressure running because I have a P3 probe looking for the pressure at the discharge LT and suction MT and making sure that that line is also satisfied. So we have a lot of internal logics to protect it. And normally what we do is we control these compressors from two different types of logics. Neutral zone when I have more than one compressor, so to avoid cycling of the compressors, and PNI when I have one only variable speed compressor to adjust the capacity and make it more precise as possible.
Yeah, makes sense.
So summer, as we mentioned, here we have this higher pressure coming from the gas cooler, transferring this energy into compression from the suction MT, and my mass flow will go partially or 100% through the ejector port of the system here. So this is where we have a lower pressure compared to the system here. Okay,
yeah,
so
makes sense.
Compared to the MT. Safety conditions, as I mentioned. So if I have all my loads empty in defrost, if I have any problem with the MT line, and I still need to have my LT line running, I have the P3 probe checking the pressure at that point and making sure that we are maintaining the pressure for the low temp compressors. I would say that in this case, P3 will always be driven by as a protection device and a higher set point to maintain things in the right conditions.
So that would mean kind of like if you get a really low load condition, all the curtains are pulled down, all the low temp cases are satisfied. And it's like, because a lot of people are like, oh, well, they worry about high temperature outside, hot days. I think I've seen more people, especially in our training programs, CO2 training programs, where it's a lot of issues are happening when it's super cold out. Like, and they don't think about that because everything satisfies and shuts off, and that's not good for a system, especially a booster system. You need something to run. So for this example, it'll be like the ejector will send some more discharge gas through the flash gas valve to keep the suction pressure up on the medium temp. Is that correct?
Yeah, so
Okay.
if you have cold and ambient conditions, like outside is colder and the cases are good, normally what you're gonna have here is that you have, let me pull here the low temperature conditions. So during the winter conditions, if you have like a very cold night, the pressure on the gas cooler will be lower. So the energy to pull refrigerant from here will be reduced or almost zero. And then the amount of refrigerant here, the ejector will be working as an HPV only, controlling the pressure.
Yep.
The liquid receiver will be always continuing maintaining the pressure here. And depending on condition, it could be almost closed. Empty lines could be closed, and due to the curtains, if it's night and so on. So all LT line will be compressing here and maintaining the pressure here based on this P3 probe. If I have a few cabinets cases on and running, it will come to this direction.
Yeah, perfect. Makes sense.
I'm not sure if I answered your question,
Yeah,
Trevor.
no, that totally makes sense.
So yeah, we foresee all the conditions, and we have tested this in Northern Europe as well. So even that ejector are not has the best effective in cold and ambience, there are some customers that they standardize ejectors because it's simple for them to have one model of systems and one only design of units. So they could install ejectors everywhere. And since the ejector can be adapted to different conditions, you don't need to take care if it's winter or cold. When it's warm and sunny, you're gonna have the effect. When it's not, it will operate as a traditional rack. So no big deal, even for the high delta temperatures that we have here in the US, that summer that are really, really hot, and winters that you can have like freezing temperatures. So no problem at all.
Something you're probably still getting used to.
Sorry?
Something that you're probably getting used to in Atlanta.
Oh yeah, we had our first snow like 3 weeks ago, and it was super nice. I came from Brazil, so I'm still playing with the snow, and I'm still finding it funny.
I love it. I love it. Okay, let's keep going.
Okay, so different conditions, the ejector will be adjusting for different behaviors. So when it comes to the ejector effect, we are maximizing efficiency with the HPV valve. And what about the flash gas? What is the role of the flash gas into this ejector world? It should operate with a fixed set point with different ones. So what we can do to improve the efficiency? Ejectors, they have a characteristic that this pressure increase from cabinets to liquid receiver, we call it lift. So the pressure that we are gaining with the ejector effect, we call lift. And we have a very curious, particular behaviors that as much lift I gain, so increasing pressure again, lower the mass flow I have. So we need to play on this with design basically to make sure that we have enough flow going through the ejector and making sure that we gain the maximum lift, so the maximum pressure increase that we can with the ejector effect. Okay, and we can control this using the flash gas bypass valve here. So with CAREL controls, what we do, we have a dynamic flash gas set point, almost similar to what we have with the gas cooler pressure, that we know that we don't have a fixed pressure set point for the gas cooler, but we have an optimal one. So the the flash gas bypass valve does the same. During summer, we will modulate it and try to find the sweet spot where we can maximize the mass flow and gaining the maximum pressure that we can. And this normally would be above 45 psi, so making sure that we have a very higher lift as possible. And during winter, what we would do is we change the logic of the high pressure valve, the flash gas bypass valve, and we will control it to maintain the pressure on the liquid receiver. So to maintain the minimum delta that we need to do to let's say, cover the pressure drop on the expansion valves here, both MT and LT. Mainly MT, since LT we have a bigger pressure delta. So the receiver management will be with a dynamic set point, and we calculate this based on the pressure on this pressure here. So we will try to maintain a lift here, always to maintain a pressure delta that would make an increase in pressure based on this pressure here. So it will be floating based on the case cabinet pressure. Does it make sense?
That makes sense. Like in the summertime, you're gonna want to run that medium temp suction closer to the flash tank, because now you got a higher suction pressure, less work on the compressor, and that's why the flash gas bypass will be open. And then in the wintertime, it's just going to be working as a regular booster system right now, high pressure valve, and the flash gas will be just maintaining that that flash gas pressure to keep flow. Perfect.
That's correct. So you can imagine that once we have the ejector effect engaged, so I have the mass flow, so all the refrigerant coming from the gas cooler, all the refrigerant coming to the ejector port, the amount of CO2 vapor here at the liquid receiver will increase, right? Because you have dual source of a vapor coming from two different parts of the system. So normally what you should do, this valve, the flash gas bypass valve, during summer, it will be fully open to reduce the maximum pressure drop that we can do here. But sometimes a valve has its limitations, so you cannot go very low in pressure drop. So what you can do, CAREL has an internal logic that we can activate a parallel solenoid valve bypassing the bypass valve. So we have here a valve that's bigger than our bypass valve and would reduce almost to zero or very close to zero the pressure drop that we are going through this valve. And this valve is activated always when we have flash gas bypass valve open for a certain percentage for a certain time, and we will make sure that at that point during summer we really need all the gas passing through these valves and reducing the pressure and increasing the pressure here at the liquid receiver. So this would make our system even more efficient because we are not expanding to compress again, we are just compressing directly from the liquid receiver. With these sequences of operation and logics, you can consider, Trevor, that all your empty compressors in your rack will be operating as a parallel line. So that's another benefit, that with this layout, with this design, with CAREL technology, you would avoid to have a parallel compressor sitting there to operate a couple hours per year. You could use your own empty compressor that's already there to be maximized this efficiency.
Yeah, and so this is more for on the manufacturer side. When you're designing with ejectors for technicians, it's just an extra solenoid to actually go around the valve, so there's less pressure drop. That's it. And so it's not a component that you've never seen before. It's just an extra solenoid. So yeah, makes sense.
That's correct. So I mean, this is the overall introduction about the ejector, and let's talk about the installation. So what should I take care if I need to replace an ejector in the field? What precautions I need to have? What are the main concerns? An ejector, from a mechanical perspective, it's really similar to a valve. I was talking to R&D, I said, oh, okay, ejector is a valve. No, ejector is not a valve, but for sake of simplicity, we can consider that it's very similar to a valve on the mechanical installation. So what precautions you need to have? When you are welding the valve, first thing, you need to weld it with a wet rag here, so to cool down the internal components. The same principle as a solenoid valve, as an electronic expansion valve, or even thermostat. This is to avoid the heat propagation inside the components and might damage it. Another main point is that ejectors are serviceable, so you basically can remove the cartridge and make the installation of the ejector without the cartridge, so you don't will deform or damage the O-rings that we have inside it. So we strongly we recommend, it's mandatory to remove it. So you can just wet rag here and then making your weldings as a traditional system. Another thing, if you are installing an ejector, it is the position. This is more for the OEM perspective on the installation side. So you should not install it backwards. You should install always the vertical or in horizontal position. Okay, so
motor up or horizontal. Yep, motor up and or horizontal makes sense. Yep.
Yeah. Another thing is that we have here an stator. So this is a bipolar motor that we have inside the ejector. We have the contacts here, and here we have a kind of a seal gasket that we have with the ejector. So once you are installing it, we strongly recommend to have the nut here well pressed to avoid any water inside this coil that would damage the coil itself, okay? So we have the right torque on the manual, but if you close it enough and you see some no void areas, this should be enough for the tightening. And last but not least, the stator, it is a bipolar motor. So we have, you can see here that we have 4 terminal connections and they are identified. You should not connect in any direction. We have a correct direction for installation. And if you can see, I don't know if you can see in the camera, but we have a pin here that is bigger than the other. So if you don't force it, it will not enter. But I have seen multiple times, you know, you are in a hurry, you didn't pay attention, and you forced it, and it will enter, will deform the connectors. But this would not be the right way to install the valve. If you install with this new model of coil, the cable will always go towards the bottom, and if you have the old model, it will always go towards the L of CAREL on the valve. So it's let's say an easy way to identify how to install it. It has the right the proper way to install the cable to the coil.
What a coincidence! All this is in the manual.
Yeah.
All of it is in the instruction manual. That's, you gotta take a look at it and follow that.
Okay. And from driver installation, what will drive the ejector? So what are the controller? I have here what we call the EVD driver. So this is a driver for bipolar motors. We can use this for CAREL or third-party valves, and it has their own display. With this device, it can be used both for superheat control, but in this case, we are using it for driving the ejectors. You can see here that I put the colors because this is another common mistake on installation. So make sure that once you have wired it, it will follow the right color sequence as indicated here. One positive thing is that when you are programming DVD, the last screen of the initial programming is the sequence of colors that you need to do with the wires. And this is one of the main points of failure in the field, Trevor. I was talking to you before. I've been to this Transcritical site last year, and I was like, I asked the people there, everything is right, is wired, it's working. Yeah, no problem. Then I start playing with the parameter because the rack was not responding and so on and so forth. And when we check it, we had a splice in the middle of the way and the cables were reversed. So when the valve was asking to open the valve, in fact, it was closing and the opposite. So we never found a good regulation point. And so making sure that you are having the right sequence of colors. If you need to splice the wire, make sure that you are following the right sequence of colors. It's mandatory to have a smooth commissioning or startup of the system.
And that goes for any electronic valve. You got to have the right wires on the right winding.
That's correct. And in this case, here again, I can have multiple ejectors connected. So I can each driver can have 2 ejectors being driven. And here we have the 2 different ports here for A and B in terms of connection. Make sure that when you are configuring, you are sure that you are driver A or driver B, depending on the application. Another important point, Trevor, is that different from our standard electronic expansion valves, ejectors, they have different number of steps. So make sure when selecting and installing or replacing the controller or the ejector in the field, make sure that you are selecting the right model that has the right amount of steps. Otherwise, you will not be opening completely or you would be overdriving the motor inside the ejector. Okay.
Yeah, totally makes sense.
And the ways of controlling the ejector. We have pretty much 2 main ways to control it. Okay, so the first one is with a 0 to 10 volt signal. So we can see here that I have the terminals I have indicated here. So when it's 0 to 10 volt and you see a wire going from GND and S2, you can identify this as 0 to 10 volt control. So with that, you can come with your meter and you can check the voltage that you have there. So it will be easier for you to troubleshoot if it's a 0 to 10 volt signal. The other way that we can do is also with serial mode. Serial mode provides more feedback from the main controller and also from the supervisory system, because I can retrieve all the alarms coming from the driver and see it on the BMS. So it's you need to evaluate what you need, or normally the OEM evaluates that if they want a easy troubleshooting with 0 to 10 volts, but susceptible to more noise, or serial mode where you can retrieve all the information. So two different ways for controlling the ejectors. Okay.
Yeah, pretty straightforward. 0 to 10 or RS485 from our system.
Yes.
Perfect.
And one last thing that I want to share, I will share this document to you, Trevor. It is a checklist for the ejector installation. Normally, we have done this for the transcritical rack, but we have one dedicated just for the ejector. So couple basic stuffs like what we were saying, the position of the ejector, the wires, how it's installed, position of the probes, and so on. So you just make sure that you have checked that everything before turning on the system. And I'm pretty sure that if you check all the boxes when you turn the system, will be really plug and play and just see the system running. Okay, so it's a good point for a document that we can share and can support the technicians in the field during commissionings.
And what's great about that is like you just go through it step by step. It's like any compressor checklist, the checklist that we do in our CO2 training programs. You go through that when you're doing a startup, because I've been to lots of startups. You go through the checklist and check everything off. Did I check this? Did I check that? That's what it's called, a checklist. And when you go through that and you said, okay, I verified this, I verified that, then you run into way less issues than be like, oh, I think I did it, or yeah, maybe it's good. You know what I mean? So always do those checklists. Be diligent.
Yeah. Okay, so with that, I mean, basic stuff, it looks like really basic, but we spend a lot of time with this in the field. So if you make sure that everything that we discussed here are properly done in the installation procedure, it should be easier for you guys to start the system. And then troubleshooting, I have added here a couple tools, basic tools that most of the technicians they have, and it could be easier for troubleshooting an ejector. So first things first, ejector position. Again, we have a three-way position, and this is just to show a picture of an installation where the customer was complaining that the ejector was not working, it was not regulating properly, and so on. So if you see here, we had a way around installation of the port. So basically, they had the ejector installed in a not correct way. So again, when we specify and put on the slide here, it's because we have seen this in the field, right? So here you can see that they were using the suction port of the ejector connected to the gas cooler. Yep. You can see that we have the evaporator from coming, the MT suction line coming from the evaporator to the gas cooler inlet port, and then going to the liquid receiver. So if you install it backwards, it will not work, and you will have a lot of troubles making sure that the system is doing well. So first thing, checking the connections, where the pipes are going. I mean, sometimes the operator reversed it, installed in an improper way. I mean, it happens. So we just need to make sure that it's connected correctly.
Yeah, it's just to verify, and that's in the manual as well. Because if you never used these before, it's like, oh, okay, well, it must go here, here, here. They're all the same port size, or they look close, similar. One question on the bottom one there. So coming out, going to the receiver, it goes almost right to a 90. Do you need any difference or differential in lengths? Should that be 3 inches or 6 inches, or is it okay just to come out like with a 90 right there like that? Is that okay?
Is that okay? I mean, after we have internally on the ejector, you will see that the piece is not so small because we have an internal piping to make sure that we have the proper fluid and fluid dynamics inside it. So when the refrigerant goes out of the ejector from the outlet, it is already mixed and in the right pressure and fluid dynamics. So from that point and beyond, you can make the curves you need. So no problem.
Perfect.
For sure, as much curves you add, more pressure drop you have. So this is more on the design side to avoid pressure drops.
Yeah, we don't like pressure drops in any systems.
Yeah. And another tool that is quite useful, let me go back to the camera, it is the magnet tool. So again, this is a bipolar motor. And if you need to make sure that, for example, the motor here inside the ejector are not locked and is not broken, what you can do is using the magnets. So the same magnets that we use for the trim expansion valve, you can use to drive the ejector. So running to one side, we are closing. I don't know if you can hear the sound here. This sound means that this click means that we came to the end of the course of the motor, and to the other side the same. So if you arrive to a place, you have your magnet, and you keep listening the clicks for both sides without moving the ejector, means that the motor is stuck inside, and most probably you will need to replace or at least open for cleaning it. Okay.
Yep.
Another good point is that you can see here that we have two O-rings, and every time that you make a decompression of the O-rings tends to dilate and would not fit and would not make the seal again. So every time you open a valve like this, it's highly recommended to replace the O-rings with new ones so you can maintain the seal inside the components. I don't have the magnets. What I could do for a quick and dirty tests. This is a magnet. So if you have a piece of magnet here, you can use the magnet to try to drive the motor. I mean, it's not precise. It is not so efficient as our tool here. But if you need to do something quick and dirty Friday, 7 p.m., you can try to find any magnet or even another valve to drive it. I mean, this is like a quick and dirty solution for Friday afternoon. And I know that it happens.
And it's the same as your other, like you said earlier, it's the same if you work on other CAREL EVs, it's the same thing. It's opening and closing it with a magnet. Fantastic.
Yeah. Okay. And another thing that you can check, it is the wiring connection. So let's say that you have a damaged wire. So our coils, all of them, they have the same resistance. So 35 ohms, from 33 to 38 ohms across all the models. So if you need to check if the coil is the problem, because you are seeing like a motor error on the display, you are seeing errors that the valve is not connected, you use the magnet to drive the valve and it's working. So it might be this piece that might be damaged. So what you can do, you can use a meter, a simple meter, to make sure that you have the right resistance. So I put here the wires, so the sequence of wires that you need to check. So in this case, for example, if you measure from brown to green, you need to read 35 ohms in that condition. If you measure brown to brown, 0 for sure. And for all the other connections, brown to yellow and brown to white, it should be 0. If you are seeing some resistance here, something is wrong with the coil, internal coil might be damaged, and you should replace this driver. So these are the combinations and the resistance that you need to read. Everything that is black means that you should not read any resistance here. It should be overloaded, so 0, not 0, so not reading the resistance here. So it's a quite easy way to check bipolar drives here, okay? Sequences of wires, again, this is something that we discussed, and what happens and if you have different sequences. Make sure that check here, because CAREL has the sequence of wires connected for poles of the stator. So 1 and 3 is the first pole, and 2 and 4 is the second pole. That's why we have 1, 3, 2, 4 sequence of wires and not 1, 2, 3, 4. Okay. Make sure that you have the right sequence, because if you reverse like brown and yellow, you are into different windings, and it means that you have motor error, so you are not able to read the coil. The controller cannot read the coil. If you simply replace like a brown with green or yellow with white, what we would be doing is like we are sending the current in the wrong direction inside the motor, and this would make that instead instead of opening the valve, we are closing the valve, or the way around. So this would generate a lot of confusion. It will not trigger an alarm because we are reading the currents, but it will drive the valve in the opposite direction. So make sure that you are properly set with that. Okay.
Yeah, makes sense.
And one just last component I want to show is we have here the EVD Ultra Cap. So Ultra Cap is a capacitor bank that we can use to close the ejector in case of emergency. So we are also covered in this point if it's needed.
Yeah, no different than the other electronic valves.
Yeah. And let's see. Yeah, and these are the points I would highlight, Trevor, from a very high level perspective. I know I
love it. I know I went way over on time. But this is awesome. Thank you for sharing that, because this is the thing. Like you may see them already, you may start seeing them, but it's diving into this to really get an understanding. It's just another electronic valve in the system. It's an added complexity because it is another component. But when you understand how it works, it makes it, where that refrigerant goes. It's about heat transfer. Where is that we moving that heat to? And just like these ejectors, you're going to see more and more of them. Understand how they work. Just like Marcel, you did a fantastic job explaining it, and I really appreciate that. We got a couple of questions here.
Sure.
What is the lifespan of an ejector? Before you answer, Marcel, I'm going to say it's probably the same as any electronic valve. You know what I mean? But do you have an idea? How long have they been running? At least 10 years, like eight to 10 years they've been running. I think it's 2016 they came out. Or how long?
Yeah, so basically what we do in terms of our manufacturing production is that all the components that we produce, mainly on the valve side, we have tested it into accelerated product life testing. So basically what we do, we have a controller opening and closing the ejectors multiple times. And basically we have ensured that during our production and also during engineering phase, the drives must be able to open and drive the valves. I think it's like 10 million or 1 billion of steps. So the amount of steps that we can convert into at least 10 years of operation. So all the components are rated at least for 10 years of operation. It doesn't mean that after the 10th year it will fail. It is just the testing quality that we do in our production, batches by batches, and we make sure that the valves will be able to drive at least that amount of steps.
Yeah, no.
And this is an estimation. I mean, we cannot say, yes, it will be that amount. If the valve stays in the same position for a long period, it would be even more.
Exactly. And how long is it? How well is it maintain the system? How, maintenance and service and install. And this goes with any refrigeration system. It's going to last a lot longer if it was installed correctly, if it's maintained correctly and serviced correctly, and they'll last longer. That's just the way it is. Another question on the horizontal mounting position. Should the suction port be positioned between 9 and 12 o'clock or 12 to 3 o'clock only?
So in this position, you mean?
Yeah. So should it be like, does it matter if the high pressure is coming into the top or into the bottom when it's horizontal mounting?
From an installation perspective, the optimal ways to install it like this, but if you need, you can install with the suction port from the top. It will be easier for installation. From the top.
Great question, Jason. Awesome. So Marcel, how can people find out more about you, more about these ejectors if they want to learn more?
Sure. We have nutref.carel.com. We have a lot of contents related to natural refrigeration solutions. This is something that we can share. I'm always available here in the US. I'm covering the whole Americas area. I have colleagues covering all the regions. I can share my email, so you guys can email me if you have any questions related to applications on refrigeration. We are always available to have a good discussion about technical topics.
Yeah, I love it. And I love having conversation with you, Marcel, because you're real technical, you understand it. And this is really important. So if you're listening on the podcast, you might have to listen to it again. Okay, go to the YouTube channel and look at the slides as the slides Marcel went through, but we talk about this in our CO2 programs all the time, just to really get a good understanding. You got to see this more and more. It's not only being here as well, listening and watching is great, but you got to go out there and put your hands on out there, you know, get that hands-on work. And that's why we do tons of CO2 training programs where you got to go out and do that hands-on work. That's where you start to learn. You learn the theory here, but you got to go out in the field. That's why I highly recommend anyone that takes our CO2 courses or supermarket programs, you learn here the theory, but you actually go out and take the action out there. So if you start seeing those ejectors out there, try to learn, investigate. Don't jump away and be like, I don't want to learn about it. Go and say, what does it do? Where's it piped to? How's it programmed? How's it controlled? How was it installed? That is so important, that hands-on portion. Marcel, thank you so much for taking the time to share your knowledge with us. If you like this podcast, please share it, comment on it. My name is Trevor Matthews. Let's get a conversation going. Thank you so much, Marcel.
Thank you, Trevor.
See you later, everyone.